Hello everyone, this is Dr. Webb. In this video, we are going to prove one of the fundamental results of group theory called Cayley's theorem, and then we're going to see Cayley's theorem in action. So here is Cayley's theorem. It's that every group is isomorphic to a group of permutations. So any group you can think of as a group of permutations because it's isomorphic to a group of permutations, which means really you can represent it as a group of permutations, because when two groups are isomorphic to each other, really deep down we kind of think of them as basically being the same group. That's how strong isomorphism is. So let's jump right in and do the proof. So let's let G be a group. Then for each element of the group, we're going to define this map L sub G. So this is left multiplication by little g. And it's defined by L little g of H is going to be G times H. We've looked at this map before. We have seen that this map is in fact a bijection on G. And so it is a permutation on G. And so then we're going to look at the set of all of these permutations built from these left multiplication maps together. And this is what our group of permutations is going to be. Okay, so G tilde, this is the set of all of these left multiplication maps, all of these permutations. And our claim is that G tilde with functional composition is forming a group. So functional composition, that's always associative. And so that immediately is checked off. If we do the composition of two of these functions, so L of G composed with L of H, so really we're doing L of H first and then L of G, this is equivalent to the map L of GH, so we have closure. So let's just verify this. So I need for any A in G, well, LG of LH of A, well, we're applying LH first, and so this is going to be LG of HA, because LH of A multiplies A by H on the left. And then when we apply LG to HA, we end up with GHA. And note that this is the same thing that we would get if we applied the map LGH onto A. And so since this works for any element of G, the two maps L of H composed with L of G and the map LGH send all the elements of A to the same place. And so they are the same map. If they send everything in the domain to, if the two maps match where they send things in the domain to the range, then they are the same map. The identity element of G tilde is going to be left multiplication by the identity. And this is pretty straightforward to see. So if you compose the identity map with any other LG, doesn't really matter the order, but let's just double check what we're talking about here. So for any A and G, if we do L sub E of L sub G of A, this is going to be L sub E of GA, which is just going to be E times GA, which is GA. Also, if we do L sub G of L sub E of A, this is going to be L sub G of E times A, but E times A, E is just the identity. So this is really L sub G of A, which gives us GA. And then lastly, L sub G of A is just going to be GA. And so you see all three of these maps return the exact same output for any A and G. So these are all three the same maps. And then if we want to do the inverse map, so this is a bijection, so it has an inverse map. Well, that inverse map is just L of G inverse. So let's double check that. So if I take any A and G, and I do L sub G inverse of L sub G of A, this gives me L sub G inverse of G of A, which is G inverse times G of A, which is just A. And that's the same thing if I plug A into left multiplication by the identity. That's E times A, which is just A. So same as before, two maps give the same output for an EG and G, so they are the same map. Okay, so this concludes the proof of the claim because we've shown that G tilde, we've shown that the operation is associative, we've shown closure, that it has identities, has the identity, and each element has an inverse, and so that means that it is a group. And so now we are going to create this map, which is going to be the isomorphism, and so it's going to be a map from the group itself to the group of permutations that just sends phi of G. G gets sent to the permutation L sub G. So our claim is that this is an isomorphism. It is onto, by the definition of G tilde, all the elements of G tilde are defined by an element of G, and so it is by definition onto. It is one-to-one if, suppose phi of G1 equals phi of G2. That means that L sub G of 1 of A equals L sub G of 2 of A for all A and G. And so then that would mean L sub G1 of A is just G1 times A. L sub G2 of A would be G2 times A. And so cancellation, right cancellation of the A's gives us G1 is equal to G2. So we have that it's one-to-one. If we compose phi of G with phi of H, right? Well, phi of G of phi of H, that is L sub G composed with L sub H. So really we're doing L sub H first and then plugging that into L sub G. Then we have already seen that this composition, when we prove closure, the composition of L of H plugged into L of G gives us L of G times H. And that is what phi of G times H is. And so this is showing that phi is preserving the group operations on both sides. Here we have composition on the left. We end up with the group operation multiplication on the right. Okay, so that completes the proof of Cayley's theorem. That's how we can from a group, form a group of permutations by just doing the permutations on the elements of the group. And then the canonical map between them is just sending the element G to what we would say the map induced by G, this left multiplication map induced by G. And this is a very natural isomorphism, and it works. So let's actually look at how Cayley's theorem works in practice. So if you're actually given a group, how do you rewrite those elements as a permutation? And so what ends up happening is that if you have a finite group of order n, then you will always be able to find some subgroup H that is within S sub n. It's a subgroup of S sub n that is going to be isomorphic to G. And if you go through the proof of Cayley's theorem, that's really what we're showing in this. So how do we actually do this? So right here we have a Cayley table for a group that's isomorphic to the Klein-4 group. And so how can we rewrite these elements as permutations? So the first thing we're going to do is renumber these elements. So E is going to correspond to 1, A is going to correspond to 2, B is going to correspond to 3, and C is going to correspond to 4. And we're going to plug those in to everywhere in our Cayley table here. 4, 3, B is 3, 4, 1, 2, 4, 3, 1, 2. And then to write these cycles, what we're going to do is we're going to think about these as permutations, almost in array format, where the top row is always our top row up here, and then the element corresponding to this, the left multiplication by our elements, are going to come from the column, and then what we the sequence we get in the Cayley table, that's going to be what would be the bottom row of the array. And so we can rewrite it as cycles. And so if we want to do left multiplication by E, well, this is sends everything to itself. And that's simple enough. So left multiplication by E, this is just the identity map. Okay, so now let's do the permutation for left multiplication by A. And so if you look, when you multiply by A, it sends the identity, which is 1, to A, which is 2, and it sends A to the identity. And so that closes that cycle. And then it sends B, A times B equals C, so 3, which is B, gets sent to C, and C, A times C, gives us back B. Okay? And so really what we're thinking about in here is that this is sort of saying E gets sent to A and vice versa. And so we've relabeled E as 1, A is 2. And then the other cycle is B gets sent to C by A and C gets sent back to B. And so we've relabeled these 3 and 4. And so that's why we have the 2 cycles, 1, 2, and 3, 4. For B, E is sent to B, and then B is sent back to E. And then A is sent to C, and C is sent back to A. And last but not least, LC, E is sent to C, and C is sent back to E, and then A is sent to B, and B is sent back to A. And so our group G tilde here, we can think of as being the 2 cycles. Well, there's the identity, and then product of 2 cycles, 1, 2, 3, 4, 1, 3, and 2, 4, and 1, 4, and 2, 3. And so this is our group. This is a group of permutations that is isomorphic to the Klein 4 group, and we are done. That is all for this video. I will see you again soon.